Hello everyone, my name is Adam Michael Anthony Simpson and you're watching my YouTube channel, Adam M.A. Simpson. This is part 2 of my episode featuring Dr. Jeremy Feaster, who is a scientist at the Lawrence Livermore National Lab and founder of the Feaster Foundation, a nonprofit that has a mission to support Black and underrepresented minority students along their paths to success and inspire as many people to serve their communities in whatever way they can. Please enjoy part 2 and yeah. Awesome. And I love how you brought up that your research, because that's what we're going to pivot into right now, which is the section on how will your work impact society. So Jeremy, please tell us of your current research work in, as you said before, electrochemical engineering and electrocatalysis. How will your research, which aims to optimize electrochemical reactors for converting CO2 to high-value chemicals, ultimately benefit or impact society?
Yeah, absolutely. I mean, I think I started working on CO2 reduction back in 2012 with, I was starting my graduate school career at Stanford. And, where I'm at now is, one of the things that I realized when I was graduating was that, we have a lot of really great scientists, a lot of great minds working on these problems. But a lot of times their focus becomes on the catalysis. It becomes on just the active material inside of a lot of these systems that does the reaction that you want. I use the analogy that, it's kind of the engine of a car. You want the engine because that's what's going to move you from point A to point B. But one of the things I realized was that, we have a lot of great engines, but we have a lot of really bad cars.
Yeah.
So we're putting a lot of great engines. We're putting the best engines in the world that we can make, and we're putting them inside of these, broken down cars. They're not really well adept to being able to do the reaction study. And one of the things that I kind of started asking in 2018 was, what are ways that we can make better cars? How do you make a car that's worthy of the engine that people are making? Or maybe if we have a better car, we don't necessarily need the most amazing engine. It's possible that, we could just have a better car, maybe, allows for us to get by with, a less expensive, much easier to make engine, and that might allow us to still be able to drive towards where we want to go. And that's kind of been the spirit behind a lot of the work that myself and so many others on my team have been able to do, is to look at taking reactor design, taking the way that we create a lot of the different chemicals that you and I and everyone really uses on a day-to-day basis, and rethinking how we design them, rethinking what it goes into those reactions and what goes into all of those systems. And that's pretty much been, kind of where I really see the paradigm shift that we've been able to start to introduce into the field, is that, we recently actually just this year published a paper showing, we could 3D print a reactor, and it's, $10. Basically make this little 3D printed reactor that normally would cost thousands of dollars to make from more conventional means. We're able to print it in less than a day, completely iterate it, completely control all the dimensions to it. And when we actually tested it for converting CO2 back into fuels, it had record performance. It was it performed just as well, if not better, than a lot of these high-end, the most advanced, sophisticated kind of catalysts and the most sophisticated systems. And that's really led us to really start challenging a lot of different chemical reactions and start thinking about how do we push the bounds. Not only just in the sense of being able to do CO2 reduction, but really when you think about it, even thinking about fertilizers, even thinking about, water purification. There's so many different aspects that these systems can kind of impact. And the other thing that I get really excited about is that at the same time, 3D printers, in the grand scheme of things, when you think about a research lab, a 3D printer is, maybe $5K. Compared to really expensive instruments that are tens or hundreds of thousands of dollars. And I have this vision of, how do we take and put a 3D printer in every high school chemistry lab that we could find and allow them to start designing their own reactors? How do we really turn the science from being something that only happens in these, bastions of science how do we turn it into something that, we start really leveraging the brilliance that sits in a lot of high school classrooms, to really start challenging the next generation of students to start thinking as researchers and start thinking as scientists, and allow them to get their hands dirty, allow them to start actually making some of these reactors, and to start really pushing the balance from and tapping into their creativity. I mean, for me, that's really kind of what for my culture, for my lab, and what I kind of emphasize for any of the projects that I'm on is, I want students to think critically, of course, and I want everyone that's working on any of my projects to think critically. You need that. You have to have that. But at the same time, I want them to think creativity. I want them to think creatively. I want them to go outside of the box. I want them to sit there and approach a problem and unassume assumptions to really branch out. And then, of course, also, I want them to think compassionate. I want them to think about, how does this help other people? How does this help society? How does this reactor that I'm working on and that I'm making, and how I'm going to be able to maybe, really the length of this project within, or the scope of the project that I'm working on, how does that impact, literally the world? Yeah. How can we use that to really start mitigating CO2 emissions, to start mitigating climate change, and to really start making a dent and making sure that we can be able to have a society that's going to survive, all these different kind of aspects that we're kind of dealing with, especially with a lot of the carbon emissions that we've been kind of generating over the past 100, 150 years.
Wow. And so you're too good at this, man. Okay. So which journal did you publish this paper in?
Yeah. So this paper was published in Energy and Environmental Science. And we're working pretty much, if anyone wants to read the paper, I absolutely encourage, we'll find a way to get the paper to you.
Yes.
To make sure that it's accessible. One of the other things that we added in there was, beyond just the abstract information, but also a broader impact. Talking about, what does this research mean to society? What does it mean to the field? What does it mean to other researchers?
Yeah.
Because to me, that's just as important as the work that we're doing, is to really be able to say, here's what we want people to take away from it. Not everyone is necessarily, spent 10 years doing electrochemical, energy research like I have, but that's okay. Like, we can still be able to say, here's the impact, here's what we're doing. And if we can't communicate that to others, and we can't communicate, what we do on a very simple, straightforward level, without having to use a lot of technical jargon or get into a lot of the fundamentals, I think we're missing a great opportunity to be able to share the research that we're doing. Yeah. I kind of emphasize that no matter what, for any student, any intern that I have, it's like, hey, talk to me like I don't know any of it. Explain it to me. For me personally, I use kind of the metric of, how would I explain this to my cousins back in North Carolina? How would I explain this to all my baby cousins who are in school and middle school and in high school that, they haven't had any exposure to this, but how do I explain it to them? How do I tell them, hey, this is what I do? Here's the research that I do. And I think that challenge has always helped me think about how to
communicate. Science communication.
Yeah, absolutely. And then also how to make it accessible. How to make sure that it's not just me talking, but them actually receiving what I'm saying and understanding.
So I'm sure your research is actually, I guess you could call it, the lens that we're seeing it through is because of, climate change, and we need to get rid of the CO2 in the atmosphere. But we can also think of it as a resource that we can recover. And you said that you can apply this to water treatment. And have you thought of resource recovery? I have another question after that.
Oh, absolutely.
Sewage water, I should say.
Yeah, no, this is something that I think we're starting to pivot and shift our attention towards a little bit more, is how do we deal with a lot of the different things that we have in wastewater, especially when you're thinking of wastewater treatment. There's a lot of things in there that we normally just consider waste, just like we normally would consider CO2 that comes out the back of your car or that comes out of a power plant that's producing energy. We used to think of that as waste.
Yeah.
We would get rid of it. We would send it into the atmosphere and say, oh, we don't need that. But now we're realizing that's a great source that we can use. Let's recycle that CO2 that we're putting out into the atmosphere. Let's turn that back into something valuable. In the exact same way, we can turn things like nitrates in water and convert that back into something viable, like ammonia. If we could turn that into fertilizer.
Or phosphates.
Exactly. Phosphates as well. There's so many different things that normally we think of as, oh, this is just wastewater. This is just something that we would put in the trash. But for me, I get really excited because we can design any chemical reactor that we need to be able to target how do we turn these waste products, these things that we previously had designated as not being valuable, and show that there's a ton of value that we can be able to extract just because we can do some really cool chemistry and we can make some really cool chemical reactors.
So do you know of Professor William Tarpey?
Yeah. Yep.
So
I know Will pretty well.
Okay, good. So I'm gonna just say, he's in the resource recovery thing, and I think you guys could have a real nice partnership with this kind of research.
I think so too.
Yeah.
I feel like Will and I have talked. Will and I have definitely talked, and I remember actually talking with Will before he started his lab, because he was a postdoc before, and we overlapped then. And there's a lot of exciting research going on. I think that there's a lot of opportunity, and the way I kind of view my role at the national lab is, I'm not necessarily I'm not trying to make the best catalyst. I'm not trying to make the best engine. But I'm trying to work with all of these other great minds, all these other great professors and students and scientists. If you make good engines, I will make good cars.
Exactly.
And we'll be able to make something really, really powerful together. And that's kind of the vision that I have, is to be able to leverage, 3D printing, to leverage all of the expertise that we've built up in reactor manufacturing and reactor design, and to say, how do we use this to make your system shine the best that it possibly can? And then give it kind of the best chance that it has in order to be able to, to look great. So
awesome. And so you did tell us this before, with the, you're promoted to staff as a PI yourself. But can you talk about that transition year? What did you learn? This, just asking, some of us are trying to be PIs someday, so I'm gonna write my notes down.
I was gonna say I keep taking those myself, because I think that's one of the things that it's been very interesting, because as a student and as a researcher, you're used to thinking, okay, I'm the one guiding the research, I'm the one in the lab doing the work, or I'm the one behind the computer doing the calculations. I'm kind of guiding a lot of work. It's a very different mindset as a PI. And that's taken a bit of an adjustment, because, for me, it's like, hey, I want to be in there. Let me go ahead and design 3D printers. Let me go ahead and get my hands dirty. And at some point you realize that, there might be opportunities for you to do that, but really your job is, how do I facilitate learning? Exactly. How do I set up everyone that walks into my lab, or everyone that walks in to do research on any project that I have, how do I position them to be successful? How do I give them as many resources as they need? How do I give them the guidance? But also, how do I give them the freedom to grow as an independent researcher? But then I think, of course, there's obstacles that have to be removed as well, but it's a completely different mindset. You're going from being the one saying, I am in the lab, I am behind the computer, I'm the one doing all of the work. And now it's a little bit more of, how do I pour into people? And so, in a lot of ways, I think of it, it's just you're building something different, but you're building something just even more valuable than any one reactor or any one system, is you're building engineers.
Exactly.
And that's exactly the way I frame it, is it's nice. Like, it's I'm building engineers. And, and one of the great things is that, all of my experience in the nonprofit space pours completely over into the research space, because now I'm mentoring. Now I'm taking that active mentorship role to say, hey, you're working on this project. Walk me through what you're thinking. One of the biggest things that I really emphasize, was that, you're not necessarily, if you do an experiment and you don't get the results that you want, it's not that it's a failed experiment. You learned how to not do something. And that is a really, really valuable thing, because at the end of the day, we're creating knowledge. As researchers on the frontiers of science, we are creating the knowledge. And that is very, very hard. If it was easy, everybody else would be doing it. It'll already be created. But the fact is, you're asking questions and doing experiments that nobody else is doing. You're thinking of problems that are, people haven't thought about before. And that's a hard process. And so you have to give yourself a lot of grace. to be able to say, I may not get this, or, you know, this experiment may not work. And that's okay if it doesn't work. To me, I always emphasize, it's okay for experiments not to work. It's okay for you to get data that doesn't make sense, or you don't fully understand. If you did fully understand it, it's not really new. You know, you're
exactly
that exists.
It can't always work, or else you're not really finding out something new. It's the same thing happened to me in my second year as a PhD student.
Yeah,
I was inherited, and I actually inherited 2 projects that I became co-first author on, thank God, under Dr. Yukako Komaki, great mentor. She was so great. But one of the projects, I noticed something that I thought I was doing the experiment wrong. And, you know, you get down on yourself, like, oh, you're so bad in the lab. But my biggest thing is, if it looks funny, repeat. And just, even if you have to repeat it 3-4 times, you'll start to see the trend. And then that's when you figure it out. Oh, I'm thinking about this in the wrong way.
Yep. This
is the result. This is new. And that's why it's special. And that's why it's contributing towards science. So I love that you said that. And on that note, like, what misconceptions of being a PI would you like to dispel?
And
let's just keep it simple.
Yeah, no, that's a really good question. The things of being a PI, the myths of being a PI. I think the one big one that I definitely have been just giving myself a lot of grace on is that you are not going to be perfect. It is not about being a perfect PI. It is not about getting every decision right. You know, I can even share from experience that, you know, even situations where, you know, you start to try to build collaborations and you start to try to create opportunities, and then you realize that, oh, you know, this isn't going to work out, or, you know, unfortunately you deal with maybe people that end up, you know, wanting to take ideas or wanting to do things themselves, and, you know, not necessarily try to get credit, or not necessarily try to incorporate you into a project. I think that, you know, one of the things that I definitely learned is that, you know, that at some point you have to decide, how do you want to do science? And it's very, very, very important that as a leader, you know, not even just as a PI, but really just as a leader, that you determine and you dictate what the culture of your lab looks like. And it's not just always about doing good work. It's not just always about, oh, I have to do, you know, the top end, you know, I have to challenge and publish in Nature and Science and everything else. A lot of it is taking the time to pay attention to the people at the end of the day, to say, if, you know, just to check in, to realize that you're teaching a holistic person that's going to have dreams, they're going to have wants, they're going to have, you know, insecurities, they're going to have things that, you know, in a lot of ways, you know, there's not a lot of training that goes into being a PI that I think could really be helpful to be able to help guide, you know, PIs to be able to help manage that, you know, where you're not just someone that's like, it's not just science. You know, it's so much more about forming relationships, building relationships, and really cultivating and trusting people to be able to do really great work, and to care about them. You know, it's not just what do they do for you. It's not just the roles that they're fulfilling inside of a project, but it's who they are.
Yeah. You know,
it's being able to speak to them and say, like, hey, tell me what's going on in your life. Like, I always ask pretty much everybody, like, how are you living?
Check in.
And what happens is people will sometimes say, oh, well, you know, this is working, this isn't working. I'm like, that's not what I
No.
Didn't ask about that. I want to hear about it. Don't get me wrong. I need to hear about the science and something. Mm-hmm. But what's more important is, how are you doing? You know, what's going on in your life? Do you need some time? You know, are you getting burnt out? Let's talk. And even if there's, you know, challenges and everything else, giving people the space to be human in a lot of different research settings is critical, because we're not machines. We're not sitting here in the lab, you know, beep, boop, beep. Here's your, you know, here's your data. We're living, breathing beings.
Humans.
We're going to have a lot of different frustrations and excitement and everything else. And your job to me, or my job and how I think of being a PI is that my job is to build the best engineer and to build the best people, because that's who's going to go out into the world and make an impact far greater than any one paper, that people are probably going to forget about in like 10 years. It's like, I'm not worried about a paper more so than I'm worried about a person.
Yeah.
About opportunities that I can take to be able to encourage, to edify, to lift up anybody, that I get the pleasure to be able to work with in a research setting.
Great. Awesome. And I think you covered a lot.
I mean, I love these conversations.
Yeah.
I mean, there's so much to cover. So.
Yeah. Well, I'm over here just saying like, oh my gosh, he's so eloquent. I wish I was like. Anyways.
Yeah.
On that note, I think I really appreciate you, taking the time to record this interview. Yeah. And the last thing I'd like to ask before ending our talk is there any way that people can see the Feaster Foundation and donate if they'd like?
Absolutely.
I'm going to include in the episode description, but I just wanted you to say, like, what's the best way to give?
Yeah, I would say there's two things that we absolutely need. Of course, one is just if anybody out there wants to donate to our scholarship fund, we're gearing up for scholarships around the country in 2021. We're doing a second round of our Justice for Breonna Taylor Scholarship. And we're also doing our Lift As You Climb scholarships for students, for Black and Brown students doing community service. So if anybody that wants to support, anyone that wants to be able to donate, they can go to www.feasterfoundation.org/donate and be able to give there. We have Cash App, we have PayPal, we have many different ways to be able to receive funding. And of course, we're a 501c3, so any donation that's given, any contribution is tax exempt. You'll receive basically the documentation to be able to report that for taxes for next year. And the second thing is, we're always looking for volunteers. Anybody that has any talents, any skills, anything that you think could be valuable, or even if you just want to learn more and figure out if there's ways that you can be able to help us, we are more than willing to be able to want to set something up and to make something work. Awesome. So if anybody wants to volunteer with us, again, you can go to www.feasterfoundation.org, be able to fill out a contact form. We'll be able to set up a meeting, and we'd love to be able to work with anybody that is just as passionate as we are about being able to amplify kind of a culture of Lift As You Climb.
Awesome. And on that note, that's it, Jeremy. Yeah. Thank you so much, and until next time.
Absolutely. It's been a pleasure. Thank you again for having me.
Yes.
All right.
Awesome. Bye.
Bye.
Thanks for watching the completion of this episode featuring Dr. Jeremy Feaster. Please like this episode and subscribe to the channel if you like the content. And see you soon. All right. Bye.